Okay, Assalamualaikum and a very good day to everyone. Okay, so this is a recorded topic, okay, for the multiple integral. Okay, so we have already started on the multiple integral, basically on double integral, right? So this time you will see in different coordinate system. So I'm going to explain on the coordinate system first before we start the double integral in polar coordinates. Okay, so this is going to show our coordinate system. Okay, coordinate system. You are familiar already about this coordinate system. Okay, so we have 2D and 3D coordinate system. Okay, 2D and 3D. So some of the two-dimensional, 2D means two-dimensional coordinate system. Okay, so we have a Cartesian that is also known as a rectangular coordinate system that is being noted by XY. Okay. Then we have another one as polar coordinate system that is being known as R theta. And we have three-dimensional. Okay. So example of the three-dimensional are the Cartesian. So we have X, Y, Z. Okay. Then we have cylindrical. And we have also spherical. Okay, the spherical has been noted by, we have X, R sin theta, R cos theta, and we have rho, phi, and theta. Okay, so refer to the dimensional system. Okay, so the one I'm going to explain for today is on two-dimensional coordinate system. That is basically related to Cartesian and polar coordinates. Okay, so when we refer to two-dimensional coordinate system, there are two variables involved, with whether it is x, y, or r theta. Okay, so problems related to the multiple integral for this two-dimensional will be called or known as double integral. Okay, and for the integral related to three-dimensional will be called as triple integral. Okay. Okay, so these are actually the summarization for three-dimensional and two-dimensional. Okay, polar coordinates here are theta, then SY is known as Cartesian. Cylindrical coordinates in 3D will be rho, phi, z. So this is the relationship into Cartesian, x, y, z, okay, in 3D. And we have here x, y, z in Cartesian 3D into spherical, r theta, phi. Okay, so this is the conversion unit. Okay, so the basic formula for double integral between Cartesian. Okay, so let's say refer here. Fxy is the function in terms of xy. Dx is the integral that we want to perform. Okay, so double integral in Cartesian given here will be equal to the one on the polar coordinates here. This is equivalent from double integral in Cartesian that is equivalent to double integral in polar coordinate system. Okay, so r cos theta is the conversion. For x, r sin theta is the conversion for y. Okay, so we can summarize the conversion as follow. Polar to Cartesian, this is the conversion x r cos theta, y is equal to r sin theta. Okay, that is come from the basic formula actually. And from the Cartesian to polar, okay, Cartesian means xy. two polar coordinates in terms of r and theta will be given here. R squared refer to the radius, okay, equal to x squared plus y squared. So r is the square root. Okay, so usually this r squared plus r squared that is equal to x squared plus y squared is the basic equation of a circle. Okay, so the angle theta here will be equivalent to the inverse tangent of y over x. So usually we noted that the angle theta lies starting from quadrant 1. Okay, so that is the rotation for the angle theta. Okay, so we are going to try problems related to Cartesian and polar as follow. The one in ebook 3, okay? Double integral in polar coordinates. So I want to explain regarding the double integral in Cartesian to polar, how we can convert it. So the problem here will be related, in this case, based on the uh, dA integral in Cartesian goes to the polar coordinates. Okay, so we'll see example 1. Okay, but here I'm going to explain example 1A and B. Okay, for example question 1A, evaluate the integrals by converting them into polar coordinates. Okay, so this is double integral. D refer to the region D. 2xy is the function in terms of xy. So dA refer to dy dx or dx dy. So we have to decide according to the problems given here. D is the portion of the region between the circles of radius 2 and 5, centered at the origin that lies in the first quadrant. Okay, so means that we have two circles that is intersect, bounded by, one is a circle that has radius of 2, and another circle is the radius of 5. Okay, so the circle we can figure out on the quadrant, based on the quadrant, that the circle centered at the origin and it lies in the first quadrant. Okay, so when we sketch the graph, okay, so we can sketch the graph actually. Okay, for example, when we have a circle that has a center as the origin, so we can figure out that the circle will be like this. Okay, so we have let's say this is a circle, then we have another circle, but this is not a complete circle because in the problem 1A just now, it lies only in quadrant number 1. Okay, so this is actually the region that we want to find out. Okay, so this is actually a semicircle, and then the radius is 2. Then here is a semicircle that the radius is 5. Okay, so because of this, okay, so everything in this x will be converted to x is r cos theta. Okay, and y is changed to r sin theta. Okay, and then the dA actually dy dx or dx dy, it becomes r dr d theta directly. Okay, so where we convert this, okay, 2x, okay, so we have 2xy, so it becomes 2, so x is changed to r cos theta. Okay, y is r sin theta. So when we have 2xy and then we have dA, then we know that dA is equal to r dr d theta. Okay, so this becomes, and when we open this bracket, so we have 2 r squared sin theta cos theta. And then for the dA, we have r dr d theta. So there's another r that we can combine. Okay, so from here, we can write it down as 2r cubed sin theta cos theta dr d theta. Okay, so r will be the limit for the radius. Okay, so because that we have region bounded by uh, between two circles. Actually, this is a semicircle. Okay, so radius 2 will be the lower limit, for the radius 5 is the upper limit. Okay, and then the angle is the rotations here. So the angle start from 0 degrees, okay, until 90 degrees. So it's up to you that whether you want to use in degree, or if you want to use radian, you can just use symbol of pi over 2. Okay. So once we identify and convert the double integral, okay, then we have this part. Okay, previously we have r cos theta and sin theta, right? Okay, 2r cube. Okay, previous one already written that it becomes 2r cube. So we just combine r and r. So the one sin theta cos theta, we have to convert into trigonometry identities. Okay, so convert it into sin to theta. So you may refer back to the um, formula list, okay, of the trigonometric identities. Okay, why we convert sin theta cos theta into sin to theta? Because we cannot integrate directly for sin theta and cos theta. Therefore, we have to convert into sin to theta, and in sin to theta we can integrate this part, right? Okay, so we perform the integration with respect to r variable first. Okay, integrate. So r cube becomes r to the power 4 over 4, and then we evaluate when r is 5 and r is 2. Okay, and then we have the constant of 609 over 4. Okay, and then next one, the next step is to integrate sin to theta with respect to theta. Okay, and then we have integrate sin theta becomes negative cos theta. Okay, but we have here sin 2 theta, therefore the integration of sin 2 theta becomes negative cos 2 theta over 2. Okay, so there's something that I want to inform you. Okay, for you to take notes. Okay, when we want to integrate sin 2 theta with respect to theta, so this will be negative 1 over 2 cos 2 theta. Okay, so evaluate when your theta is 0 and pi over 2. There is a constant here, so later on you can combine. Okay, please make sure don't write down like this. Okay, don't write down cos 2 theta over 2. I don't suggest student to write down like this, because usually when the student write down, then they just cancel these two. Okay, we cannot cancel out because there is some constant. The other one is the angle. Okay, so once we simplify, okay, you will get 609 over 4. Okay. Okay, next we goes to example 1b. So this is our function e x squared plus y squared dA. The region is the unit circle centered at the origin. Okay. So we don't have any different limits. Okay, so we have here standard equation of the circle x squared plus y squared. So no information of the radius. If it's centered at the origin, and then we assume that the radius will be equal to 1. Okay, we need to determine what is the angle, because in previous one example in 1a, we know that it is a semicircle, therefore the limit for the angle is 90 degrees. Okay, that is equivalent to pi over 2. Okay, this time there's no limits. We assume that it is a complete circle, so means we have from quadrant, the angle that is comes from quadrant 1 and reach until quadrant number 4. Okay, so means that the angle is 360. So in pi radian, it will be written as 2 pi. Okay, so that's the limit. Okay, so similarly, we have double integral in terms of Cartesian here. Then, so this dA refer to dy dx or dx dy. Convert it into polar coordinates. So this dA becomes r dr d theta, and then x squared plus y squared must be changed to r squared. Okay, because standard equation of the circle is x squared plus y squared that is equal to r squared. Okay, so previous one we already determined that the radius is from 0 to 1. Okay, take note that the radius cannot be negative, yeah. Okay, the angle is from 0 to 2 pi. Okay, so, and then you can perform the integration. Uh, the first step here, after we convert into the polar coordinates, r e r squared. Okay, so this time we are using um, special method to integrate that we call substitution method. Okay, so this one, the techniques of integration you must familiar already. Okay. And then evaluate, substitute R1 and R0, find the difference. After that, we integrate with respect to theta, then becomes theta. Okay, and then just combine it. Okay, so then we have this part. If you are not clear about how to perform the integration for this question 1B, okay, please contact me. Okay, please ask me. Okay, so the next example that I want to explain is on example 3. This is actually related to the volume problem. Okay, so I'm going to read the question or the statement. Determine the volume of a region that lies under the sphere x squared plus y squared plus z squared that is equal to 9. So this is actually the curve, okay, the curve of the equation for the sphere. Okay, above the plane z0 and inside the cylinder x squared plus y squared that is equal to 5. Okay, so means actually we want to evaluate the double integral for the volume problem. Okay. Okay, so to evaluate the volume means that we are applying double integral for the function like this. And then we need to convert it into polar coordinates. Okay. So this z equation, z squared expressed as a subject, then we have this kind of equation. Okay, this comes from the um, this equation, transform it, and then we have z equal to square root 9 minus x squared minus y squared. Okay, so that is the equation for z. We express the z, and then the next step is to determine. Okay, this is actually the sketch of the volume problem. Okay, the graph of the volume problem. Okay, we have the curve for this equation that is x squared plus y squared plus z squared. Okay, and then we have another solid. Okay, let's say we want to find out what is the radius. Okay, limit for the radius will be 0 until square root of 5. Where we get square root of 5, okay, where we get the square root of 5 comes from this one. So r squared is equal to 5. R is 5. R squared is equal to 5. So then R is square root of 5. Okay, next find the limit of the angle. So we have still between equation of a circle. So from quadrant number 1 to quadrant number 4. So the limit from 0 to 360. So 360 is equivalent to 2 pi. Okay, so we have this equation, double integral in this function. This is in Cartesian. Okay, xy. Okay, so this one convert to the polar coordinate, it becomes this one lah, r squared. Okay. So this dA becomes r dr d theta. Okay, r dr d theta refer to dA. Okay, so previously we already identified that the radius is from 0 to square root of 5 and the angle theta has its limit from 0 until 2 pi. Okay, then we can perform the integration like this. Okay, so if you are not sure what is the technique that we use here, then ask me. Okay. So the integration you are supposed to know already how to integrate them. Okay, so I have explained about double integral from Cartesian to polar coordinates. Okay, so this time we are going to see triple integral in the Cartesian coordinates. Okay, 3D coordinates. Okay, so triple integral. This is notation. This integral for 3 times. So we have the function. Uh, if it's in double integral, usually it will be written as dA, but for the triple integral, it will be written as dV. So we have three axes that we want to perform the integration. Okay. So in the Cartesian, we have dx, dy, dz refer to the dv. Okay. So AB is the limit for x-axis, CD is limit for y-axis, RS is the limit for dz. Okay, z-axis. However, we can perform sometimes. We can have, let's say, dy, dx, dz. Okay, or we can have the triple integral as dz, dx, dy. So we have to change the scale according to the axis. Okay. Okay, it's very simple. I will just explain example one because this is direct integration for the Cartesian in three-dimensional system. Okay, we have this triple integral 8x y z dv. So this is the limit. 2, 3 is the limit for x. 1, 2 is the limit for y. Z is uh, dotted by the limit 0, 1. Okay, so all we have fixed limit, right, for x, y, z. Okay, so we just need to substitute. Okay, because that we have fixed limit, this is x, y, and then there is a z. So there's no problem whether you want to use dx, dy, dz or dz, dx, dy. So the one in the ebook, they are using dz, dx, dy. Okay, so the most inner, this is the most inner, is z-axis. Okay, so the limit here, the inner part must be limit for z. Okay, next we have the middle one, limit for x-axis, dx. So this is the limit for x-axis. Okay, the outer one is the dy. So this is the limit for y. So we have to sort according to the axis. Okay. So 8x, y, z. So everything is being conducted in Cartesian. Okay, x, y, z axis. So we just do direct integration. Okay. So first integrate with respect to z. So we have z squared over 2, right? So simplify with 8, then we get 4. Okay, and then substitute z1 and 0. Okay, next integrate with respect to x. Okay, then we have x squared over 2, then you can simplify. And then substitute when x 3 and 2. Okay, and then integrate with respect to y. And then substitute y is 2 and 1, then we get 15. Okay, so the answer for this triple integral is 15. Must be the same answer whenever we change the axis. Okay, let's say we are evaluating the triple integral based on dx, dy, dz. Okay, so you must get 15 as the final answer also. Okay, you cannot get a different value from this. Okay, so we continue to the triple integral in Cartesian based on the dv. Okay, so here is the dv in triple integral dv in Cartesian. Okay, so this is example 2 problem. So let's see how we can solve the triple integral. Okay, evaluate triple integral 2x dv where E is the region under the plane 2x plus y plus z that is equal to 6 that lies in the first octant. Okay, so if it's in two-dimensional coordinate system, we call as first quadrant. So if it's in 3D, then we call as first octant. Okay, so the term must be changed. So quadrant in 2D, so in the 3D is called as first octant. So first octant means that it is a two-dimensional coordinate system that can be divided into 4 quadrants of three-dimensional coordinate system. Okay. Okay, so first octant refer to the first quadrant when all three coordinates are positive. Okay, we have this equation 2x plus 3y plus z. This is actually a straight line equation, but containing three variables, okay, between three axes. Okay, so the figure you can find out, this is the figure for the graph. Okay, this is the graph of the equation. Okay, so how we get this 3, 2, 6? Okay, so we have to imagine if we have three axes x, y, z. Okay, so you can just let two axes equal to 0, then you get another points, right? So this is when y and z is 0. So we have point x equal to 3. Okay, this is when z and x equal to 0, then we have y equal to 2. So similarly, we have this point. Okay, so just draw a straight line between these 3 points, then we get like this figure. Okay, so the point here will be, this is the origin 0, 0. Okay, this is the point 3, 0. Okay, this is the point. This is if we have in terms of x, y axis lah. Okay, this is x0, y0. This is 3, 0. This is 0, 2. Okay, if it's between two axes, x, y. Okay, so we are interested to do this kind of equation, this figure. Okay, so the one of the straight line here, the red one, we have equation here. How do we get this equation? You can formulate based on the straight line equation, y equal to mx plus c. Okay, so find out what is the gradient. Okay, so from the graph we can see that the gradient m is negative 2 over x. C is the interception at y-axis. So this is the value of c. Okay, so we just write down. This is in terms of y as a subject. That is also equivalent to this equation, x as a subject. So the two equations are the same, only the subject is different. Okay, you can modify it. Okay, so when we want to evaluate the triple integral, okay, so the dv, so we have the one that we have unknown limit, okay, we do not have fixed limit is the z-axis. Okay, so the z-axis will be the inner part. The other one, dy dx or dx dy will be outer one. Okay, so that one will really decide later whether we want to use dy dx or dx dy based on the limit. If it's fixed limit, then the x-axis containing the fixed limit, it should be the outer one, okay, not the inner one. Okay, so 2x dv, we find out first the z-axis limit. Okay, so we get here from 0 to this equation. This is the transformation from our uh, z equation. Okay, z equation. 6 minus 2x minus 3y. Here, the modification from this part. Express z only. Okay, so that is the upper limit. So we don't have fixed limit actually. We have in terms of function, right? So this one, 0 is a fixed value, but the one that I mean here, 6 minus 2x minus 3y, it is in terms of function limit. Okay, so the z-axis should be the inner one. Okay, and then between y and x-axis, okay, so we are refer to the limit for y. Okay, we have okay, if we have decided that we want to set x-axis from 0 to 3 as fixed limit, so x-axis will be the outer one. And then the y-axis will be our region here. Okay, so the equation represented for this, the equation, the line, the red line here, okay, will be either one. We are going to use the function in terms of um, x variable, express this one, y as a subject. Okay, so this will be your this will be our upper limit for dy. Okay, lower limit will be from 0. Okay, so next, substitute all the limits. So this is the limit for from 0 to negative 2x. So this is from y0 until y here. So this is upper limit for y, but we do not have fixed limit. It is in terms of the function. Okay, fixed limit only x-axis from 0 to 3. Okay, we have two choices here for dy dx. In this case, I'm using dy dx. Okay, this ebook using dy dx. So this will be, the inner one will be the limit for y. So the outer one will be the limit for x. The most outer, there must be a fixed limit. Okay, fixed limit like this lah. X is 0, x is 3. Okay, fixed limit. But why? Here, not fixed limit at the upper one, right? Okay, so we can use dx dy also. But if we want to change dy dx to dx dy, so of course these two you must change the limit also. Okay, so if we want to change the limit into dx dy, okay, so therefore we are using here this part. Okay, so the outer one, okay, dx dy change to dy dx change to dx dy. So the outer one will be the limit for y. Limit for y will be from 0 to 2. Okay, that is here from 0 to 2, limit for y. So this must be limit for x. So x is from 0. So this upper limit function must be changed. So we are going to use this one. Negative 3 over 2y plus 3. Okay, that is the another method. Okay, after that, perform direct integration. Okay, between dz and then dy dx, and then you'll get the answer is 9. So if we change just now, okay, after this part, if we change this one into dx dy, you must get also the value of 9. Okay, so you can verify the methods later on. Okay, so I think that's all for today's topic. Okay, we will see on the next class.